The number of road traffic deaths continues to increase, reaching at least 1 million people die every year because of car crashes. At least 25% of car crashes have been caused by driver distraction. A driver distraction could be visual, like if he took his side of the road. A driver distraction could be manual, if he's texting or talking to a passenger. A driver distraction could be cognitive, if he is not a stable state of mind. Many solutions were provided to eliminate this dangerous problem. Forward collision warning, which use a sensor in front of the car to alert the driver if the car reaches a specific distance before the collision. Other solution: automatic emergency braking, which engages a braking system if there is a potential collision. Other software solution is provided by iOS 11 is to set your iPhone on a don't disturb mode so you don't get distracted by the notifications. Our project aims to reduce total number of car crashes by detection and elimination. What's interesting about our project is that while enhancing, we kept in mind the end goal of the project, which is to create a standalone business product that works offline. The driver action classification model is to detect the driver actions and see if he's distracted or not. The HeadPose model is to detect the driver's head angles. The speech recognition model is to convert the driver command into a transcript to go through the fourth model, which is text classification model, to start classify the command and do what the driver wants.
In this model, we take a photo from a side camera and output what action the driver is doing. We at first use the State Farm driver distraction dataset, which contains 22.4 thousand labeled photos of 10 classes. The classes like safe driving, drinking, texting, and so on. With understanding what needs to be achieved, we designed the vanilla model, and surprisingly, we gained 99.6% accuracy. But of course, at real-time testing, the accuracy was disappointing, as there was data leakage due to multiple photos for the same driver doing the same actions. So, we decided to split the data by driver ID. After training the new splits on the same architecture, we only gained 30% accuracies due to underfitting. So, we used transfer learning using ResNet 50 and froze 50% of the layers and tuned the model using a small learning rate with small batch size to add regularization effect. Also, we added L1 and L2 regularization, dropout, and augmentation to prevent overfitting, in addition to using the AUC driver distraction dataset, which contains 17.3K photos of the same classes. The final model accuracy is 95.5%. In the second model of the detection models, it takes a photo from the frontal camera and output the pose of the driver. By predicting the angles of the face in the 3D space, the three predicted angles, which are yaw, pitch, and roll, helps us to tell if the driver is focusing on the road or sleeping, and so on. We used the 300 WLB dataset, which contains 61.1K photos to train the model, and the AFLW 2000 3D dataset to test the model. First, the photos go through phase detector as a pre-processing step. Then the photos enters to Resonance 50, in which the architecture is divided into 3 branches, each branch responsible of one of the 3 angles. Each branch classifies its angle to 66 class. Every class is 3 degrees, as a total of 198 degrees, from -99 to 99 degrees. Then we use regression to predict more accurate angle between those 3 degrees. The mean absolute error is 6.21 degrees.
We will use DeepSpeech as our ASR as its own source, so adapting and changing can be made to meet our specific problem. DeepSpeech also provides regular updates, helping community and the adaptation to state-of-the-art technologies in ASR. They also provide a trained, ready-to-use model without training, as the model training requires powerful GPUs and much time to train can be up to a month, and also it have a huge benefit of running locally without internet. To wake up the voice system, we will use trigger word like activate to start the ASR model. We use trigger word system instead of always using ASR model because ASR is much more computation extensive. So we use the simpler trigger word system to activate the ASR model only when needed. Then after waking up the system, the model will start to listen to the driver command until the driver stops talking. The model converts the voice to text, then the text will be fed to the next model to convert it to car functions. This model architecture converts the voice to spectrogram frequencies to get the most important frequencies regarding to human voice. Then the spectrogram is divided into parts with a small intervals of time, like 10 milliseconds. Then these parts is forwarded to fully connected layers and an RNN to predict the character in each time interval. After that, the repeated characters are removed to form a correct word. Sometimes the generated word can have some misclassified characters, so the use of language model can help to generate the closest right word. And also it has some statistics about the relation between words, so the model can generate a sentence that makes sense. We created our own language model by training it on car commands that will be used by the driver to specify the vocabulary to our own use case and make the model perform better to our problem.
Each word of the sentence is converted to a word of numeric values. The vector TF-IDF downscales weights for words that occur in many sentences and distinguishes the important words of each class. Then words are fed to the classifier. Since we couldn't find a dataset that fits our own solution, we created our own with over 400 sentences and 10 main clauses, which wasn't enough. So we used augmentation techniques of EDA, which provide synonym placement, random insertion, random deletion, and random swiping. As some sentences may have some values like set the air conditioner to 25 degrees, we needed to recognize these values using named integer recognition, provided by Spacey to recognize these values. So the model will produce 3 signals: the device signal, the command signal, and the value signal if needed. After producing the corresponding text of the voice produced from DeepSpeech, we'd like to classify the sentence of specific car device and car command, like open the radio.
We intended to install our system to a dedicated Jetson Nano GPU board, but due to COVID-19, we shifted to test our system on CPU and compress the whole system to get an estimate of how driver action classifier, HeadPose Model, speech recognition, and text classifier work, and the results were satisfying in real time. To sum up the system, a driver would activate the NLP models using word activate. Then the speech model would wait for any command to analyze it and send it to the text classification model to generate a specific car device signal with its own command. Two cameras follow the driver continuously. One of them takes a side view of the driver, send it to the driver classifier model to detect if he is safe driving or doing an action that impedes him. The other camera takes the driver face view, send it to the HeadPose model to detect if the driver focuses on the road or not.